Dr. Smee, I always appreciate the opportunity to catch up with you here at Mobile World Congress about all of the foundational wireless research you and your colleagues at Qualcomm are doing. So maybe let's start with the two big buckets here, coverage and capacity.
Yeah.
So on the coverage piece, if the goal is ubiquitous connectivity, it's going to be more than terrestrial networks, right? We have to have an integration with TNs and NTNs. So maybe tell us a little bit about the work you're doing in that area.
Yeah, so the first big thing is like, how can we get the most value out of the spectrum? And so if we look at the lower band, so these are bands below 1 gigahertz or between 1 and 2 gigahertz, that lower band FDD spectrum, it's so important to bring a lot of improvements. And as we went from 4G to 5G, FDD didn't change a lot. There was a lot of focus in 5G on enabling, for example, 3.5 gigahertz, 28 gigahertz, but those low bands did not get as much attention in terms of new design. So as we're looking at 6G, we're bringing a lot of innovation into those lower spectrum bands. And at the same time, we're saying, hey, what can we do better from a coverage standpoint? Recognizing that uplink traffic, your ability to connect well between the device and the network, there's going to be a lot more user-generated content, in my view, that's going to need that uplink performance and that coverage, so you're getting those uplink data rates deeper and farther into the network. We're also always looking at, the evolution of satellite networking. So, NTN was a big topic. It was in release 17 of the standard, and Qualcomm's done some interesting R&D trials with other industry players on NTN. And so we're kind of taking that forward, looking at what we call, integration of terrestrial and non-terrestrial networks. But first and foremost, the goal is to extend that network coverage on the ground, leaving those cell sites to go even further. And at the same time, making sure we're doing the standards work necessarily to have that, integration between terrestrial and non-terrestrial.
All right, very good. And then on the capacity piece, I guess high level, it's about making the best use of the spectrum that you have access to while preparing to deploy new spectrum. So to that point, how are you all thinking about system level enhancements to MIMO design as we start to look at the upper mid-band?
Sure. Yeah, when we look at upper mid-band, so we'll look at, for example, 6 to 7 gigahertz, around 7 to 8 gigahertz, a lot of focus on taking that antenna technology, that MIMO. So in 5G, one of the big buzzwords was massive MIMO. So in a given base station antenna, you could have a large number of antenna elements. When we go from 5G to 6G, we're going to be scaling that massive MIMO to giga MIMO. So as an example, the spectrum goes twice as high, 3.5 to 7, but we can get 4 times as many antenna elements in that same area. That enables us to have better beamforming on the network side to extend that coverage. And same thing on the device side. We'll be increasing the number of antennas to enable those 6, 7 gigahertz cell sites to be macro cell. You're going to leverage your existing footprint on the network side, and yet you're moving to an even higher frequency with this giga MIMO upper mid-band around 6 to 7 gigahertz. That's going to be really important to bring more capacity into 6G. And as you're seeing on the show floor today, so much focus around how AI is transforming telecom, mobile, applications, compute. It's also really transforming how people interact with devices. We're in the really early stages of AI and generative AI. As we look forward to agentic AI and kind of getting that increased scaling, there's going to be even more needs for uplink traffic, downlink traffic, so that capacity of cellular is going to be huge needs in that 2030 6G time period.
And I know you've got a long list of research priorities. I was curious if you could kind of focus in on this idea of a digital twin network and then combining that with AI to kind of understand how we continue evolving towards 6G.
Yeah, so a digital twin is an interesting technology because it's about modeling. And we've been modeling wireless communications systems for a while. But the question is, how precise are you modeling them? Are you modeling because you have a good statistical model, you've got your kind of data processing done, and you understand the mean and the average and the distribution? But the point of digital twin is you're actually getting into that reconstructing, your ability to predict and really get that full RF understanding of the environment. So we have an interesting R&D program taking a digital twin of the network. And then we're able to do that AI optimization, taking it to the next level of a very kind of specific end-to-end performance leveraging AI. And so that digital twin has an interesting option. On one hand, it could be enabling a new service. For example, you're getting a RF sensing and understanding of the physical environment. It also enables the network itself to optimize it better because it has a better understanding of the environment. So we see it as kind of two-sided operation side, and then also an interesting use case in and of itself.
You mentioned RF sensing there. I'd like to kind of click in on that. There's a few demos out here about integrated sensing and communications, and that's been a topic that's come up a good bit during the show for me. What does it really imply when we have a communications network that's more than a communications network? It's also something that's understanding the changes in the physical world around it. What do you do with that technology?
Yeah, so that when we look at the understanding the sensing, so first of all, we're communicating over relatively wideband signals as part of 5G. So the signals are wider, we can get better temporal resolution in time. It enables us to better understand the environment. So the point is, when we look at the network itself, you can view it as all these different cell sites, and you have all these different devices. And so we're able to use, for example, RF sensing to understand that physical environment. So that enables us, for example, we could be tracking a drone. We could be using the signal to do that, kind of range finding, kind of like radar. And when we're looking longer term at the 6G timeframe, we're saying we want to make sure when we're designing 6G, it's not just for communications. So we're designing a waveform. Hey, how do we make sure that waveform can do positionings, can do ranging? So that's the integrated part of sensing and communication. But it also opens up this new door that, hey, the network is able to do that sensing of the environment. It can leverage technologies like subband full duplex, so it can be listening as well as transmitting on the network side and get that RF signature. So for us, it's a really interesting one. We have a couple of different technology demonstrations today talking about, hey, how can RF sensing translate into a use case? How can it be meaningful for an operator? And then how is it also leveraging some of the advanced 6G techniques?
So in terms of 6G and AI, I've heard this descriptor used as AI native. So I just wanted to hear from you, what does that mean exactly, and how does it figure into the way you all approach your research and development?
Yeah, so 6G is, in our view, as we say, it's going to be AI native. So what that means is it's not just about having AI in the device and AI in the network. It's also a fact that AI is going to be in the air interface itself. So next week I'll be at the RAN workshop for 6G, that kind of kickoff on the global 6G standard. There's going to be a lot of different contributions about, hey, how could AI improve the design and actually impact the specification of 6G? So when you say 6G is AI native, it means AI is actually baked into the specification of how devices in the network are communicating. And that's going to enable new levels of performance, whether it's channel state feedback or whether it's how we're looking at the end-to-end software stack, understanding what the traffic flows are, understanding how can we do a better job on security. So it's interesting how AI is an application. It's part of the toolbox for any engineer today. And it's also something that from a standard standpoint, we can bring AI directly into the standard.
Well, I hope that this time next year, we can get some updates on how the standards are progressing. But in the meantime, you and your colleagues are doing some great work on the R&D side, and I always appreciate you taking the time to give me an update on it.
Yeah, thanks very much. My pleasure.